Hello, my name is Khalis Danial from M5T25. In this video, I will discuss about isomerisms in organic compounds and mutually complete my assignments. Without wasting time, let's moving on. Isomerisms in organic compounds means the compounds with the same qualitative and quantitative composition of elements. Therefore, their relative molecular weights and general formulas are identical, but their structures, including in the 3D arrangement, are different. For examples, the compound butane and isobutane are isomers since they have the same general formula, but their 3D arrangement is different, whereas the compound propyl chloride and propane are not isomers since their qualitative composition of elements are different. Same goes as propane and propene. Only one compound or many compounds may have the same general formulas. For example, methane, a linear saturated hydrocarbon, is a single compound without isomer, while pentane has 3 isomers. A line saturated hydrocarbon with 40 carbon has more than 62 trillion isomers. As we know, isomerism in organic chemistry is a phenomenon shown by 2 or more organic compounds having the same molecular formula but different properties due to difference in arrangement of atoms along the carbon skeleton, or structural isomerisms, or in space, or stereoisomerisms. The chart summarizes the type of isomerisms, but we will discuss both stereoisomerisms and only chain positional and functional isomerisms under structural isomerisms. The first isomerisms that I will discuss is structural isomerisms. Structural isomerisms or constitutional isomerisms is a form of isomerism in which molecules with the same molecular formula have different bonding patterns and atomic organization, as opposed to stereoisomerisms, in which molecular bonds are always in the same order and only spatial arrangement differs. There are multiple synonyms for constitutional isomers. There are 3 categories of constitutional isomers. Those are chains and skeletal, positional, and functional isomers. Positional isomers are also called regioisomers. The first type of structural isomerism is chain isomerism. In chain isomerisms or skeletal isomerisms, components of the usually carbon skeleton are distinctly reordered to create different structures. For examples, pentane exists as 3 isomers, often called simply pentane, isopentane or 2-methylbutane, and neopentane or dimethylpropane. Second example, we could see there are 2 isomers of butane. In one of them, the carbon atoms lie in a straight chain, whereas in the other chains is branched. The second type of structural isomerisms is positional isomerisms. In position isomerism or regioisomerisms, the basic carbon skeleton remains unchanged, but functional group or other substituent change position on a parent structure. For examples, there are 2 structural isomers with the molecular formula C3H7Br or 1-bromopropane. In one of them, the bromine atom is on the end of the chain, whereas in the other it's attached in the middle. Another similar examples occurs in the alcohol, such as C4H9OH or butyl alcohol. Consider the molecular formula benzyl chloride. There are 4 different isomers you could make depending on the position of the chlorine atom. In one case, it is attached to the side group carbon atom, and then there are 3 other possible positions. It could have around the ring next to the CH3 group, next but one to the CH3 group, or opposite to the CH3 group. Next, the third type of structural isomerism is functional isomerism. It is a very interesting form of isomerism where the compounds are different due to the different arrangement of atoms leading to different functional groups. It's are structural isomers that have the same molecular formula, that is the same number of atoms of the same elements, but the atoms are connected in different ways so that their groupings are dissimilar. These groups of atoms are called functional groups or functionalities. There are several examples of functional isomerism. First, a molecular formula C3H6O could be either propanol or aldehyde or propanone, a ketone. Another common example is illustrated by the molecular formula C3H6O2. Amongst the several structural isomers of these are propanoic acid or a carboxylic acid and methyl ethanoate and ester. Those are for structural isomerism. The second type of isomerisms in organic compounds is stereoisomerisms. Stereoisomers are a type of isomer where the order of the atoms in the two molecules is the same, but their arrangement in space is different. To understand this, we need to take a look at the ways that organic molecules can and cannot move. Again, using a three-dimensional models is a great tool to visualize this and almost essential for most people to grasp this concept clearly. With cycloalkanes, we observe that a group placed on one side of a ring stays on the same side. Except in very large rings, the carbons are not free to rotate all of the way around their axis. This means that a group that is axial will not move into an equatorial position, and vice versa. Stereoisomerism is the arrangement of atoms in molecule whose connectivity remains the same, but their arrangement in space is different in each isomer. There are two types of stereoisomerisms. Those are diastereomerisms, including cis-trans isomerisms, and optical isomerism, also known as enantiomers and chirality. First, I will discuss about cis-trans isomerisms. Cis-trans isomerisms occurs when a double bond is present because the pi bond involved prevents that bond from being twisted the same way that a single bond can be. Molecules are stereoisomers because the two carbon atoms cannot be rotated relative to each other due to the rigidity caused by the pi bond between them. Therefore, they are not superimposables. They are not identical and cannot take each other's place. However, the isomers are not mirror images of one another, so they are not enantiomers. Therefore, they must be diastereomers. There are two forms of these isomers, the cis and trans versions. The form in which the substituent hydrogen atoms are on the same side of the bond that does not allow rotations is called cis. The form in which the hydrogen are on the opposite sides of the bond is called trans. Molecules below shows the example of cis-trans isomerism. The two molecules shown above are cis-1,2-dichloroethane and trans-1,2-dichloroethane. The second type of stereoisomerisms is optical isomerisms. Optical isomers are stereoisomers formed when asymmetric centers are present. For examples, a carbon with 4 different groups bonded to it. Enantiomers are two optical isomers. Every stereo center in one isomer has the opposite configuration in the other. Compounds that are enantiomers of each other have the same physical properties except for the direction in which they rotate, polarize, light, and how they interact with different optical isomers of other compound. In nature, most biological compounds such as amino acids occur as single enantiomer. As a result, different enantiomers of a compound may have substantially different biological effects. When a molecule has more than one source of asymmetry, two optical isomers may be neither perfect reflections of each other nor simple impossibles. Some but not all stereocenters are inverted. These molecules are diastereomers, not enantiomers. Diastereomers seldom have the same physical properties. Optical isomerism is a form of isomerism, specifically stereoisomerism, where the two different isomers are the same in every way except being non-superposable mirror image of each other. Optical isomers are known as chiral molecules. Figure below shows butan-to-all. Butan-to-all is the example of optical isomerisms. The asymmetric carbon atom in the compound, the one with 4 different groups attached, is often shown by a star.